thank you for inviting me to come and inviting me to give this talk. And it is interesting to remember Fred, as was mentioned. I was a graduate student when I first knew him. He, I think, was teaching, had a job at Northern Illinois University at the time. And so he was around Chicago a lot, so saw him a lot. Oh, what's that? Oh, okay. And yeah, so what we know, what we don't, what we know and what we don't has maybe changed after I read an email this morning significantly. So that's sort of, I got an answer from Robert Birkeland to an email I sent him in the end of May. And this morning I was having a cup of coffee at this place on Bloor Street. There's a cafe, and decided to look at my email. Whoa, okay. Anyway, so that's sort of interesting. So maybe we know more than, at least somebody knows more than I thought, which is sort of cool. So let's see. So this is an old problem in equivariant topology. First of all, the new stuff will be, my contribution is joint with my last graduate student, Chris Lloyd, and also with William Balderrama, who was a postdoc at Virginia and is now a postdoc in Bonn. And so this is just some notation. I want to study actions of finite p groups on spaces. Okay, so p is a prime. If I have a cyclic group, C p to the k is a cyclic group of order p to the k. Sometimes I use the term finite G spaces, and so I kind of think of it as like a finite GCW complex, but maybe I want to allow more. I want it to be something that looks like a finite GCW complex in the G equivariant homotopy category, so it doesn't even have to be compact. And maybe I want to allow retracts of such things. And maybe I want to even just look at prime P. So these are the guys that if I took equivariant suspensions of them, they would become the compact objects in the world of G equivariant stable homotopy. Okay, so these, if you, anyway, so we'll be discussing a little bit of that later. Okay, so anyway, those are the things, but it includes classic things. I'll use that notation for the fixed points. Okay, so here is a problem. How is the homology of fixed points related to the homology of X? Okay, so very classically, homology meant mod P homology. And in the last 10 years, we suddenly have theorems where mod P homology is replaced by Morava K theories. And it's a very, very interesting question. So this is a short talk, and so I'll be stating theorems. I won't have time, just like the last talk, to do much with applications and things like that. But there'll be references at the very end, and I hope some of you will explore some of those papers. So here are two classic theorems. So okay, a space is mod P acyclic if the map from a space to a point is an isomorphism in mod P homology. Okay. So here is one of the oldest theorems in our subject. Maybe versions of it go back to the late 1930s. P.A. Smith says, suppose you have a finite dimensional CP space. And if it's mod P acyclic, then the fixed point space is mod P acyclic. And so this statement is pretty much in a paper in 1941. Okay, so this was classic when I was a graduate student, which was a pretty long time ago. So it was sort of considered really classic stuff. So here's an upgrade. Ed Floyd, who I had the pleasure of being a colleague with for a few years in the late 1980s, proved the following upgrade, and the publication date is 52, pretty soon after his PhD. If you have a finite dimensional space with an action of CP, the total dimension of the fixed point space will be less than or equal to the total dimension of the homology of the original space. And so, so you're learning something about every space with a ZP action, right? You're getting a condition, you're learning something about every single space as long as the homology, I guess, wasn't infinite dimensional. So again, the hypothesis for these things was that the thing be a finite dimensional, let's say CW complex for simplicity. Okay, so now we want to talk about versions of this with Morava-K theories instead. So I'm just going to remind you what Morava-K theories are. The complex-oriented, that's cool. Since they're complex-oriented, there's an associated formal group. Their formal group is height n. K0 is rational homology. Kn has that as its coefficient ring. It's Laurent polynomials on periodic and all this. In particular, K1 is complex K. It can be thought of as, well, it's equivalent to complex K theory with mod P coefficients. Okay, certainly at the prime 2 it's that, and otherwise it's equivalent to it for our purposes. So this is useful notation. I want to talk about a lot of dimensions. So since the coefficient ring is a graded field, you might be, every graded fields have bases, so you can talk about their dimension, and these will always be finite dimensions. So finitely generated free modules over the coefficients. So that's my notation. Okay. So here's a theorem from Doug Ravenel. He showed if in the late 70s, it's in his conjectures paper, the proof, I guess, if X is a finite, finite spectrum, but it could be finite space, the CW complex just, if it's Kn plus 1 acyclic, it's acyclic in the previous one. So if something is, K1 acyclic, it's rationally acyclic and stuff like that. So this is a classic thing. And if you look at his paper very carefully, I mean, I don't know how many people read the proof, but he actually showed that the dimension goes down as you move along the lines. Okay, for any space. So that's kind of interesting. It looks a little like some of the things in the Smith theory situation, right? So and Steve Mitchell also in the early 80s, there exists spaces of all types, right? A space is called type n if it's acyclic in the previous ones, and it's not acyclic in the nth one. Okay, so this is sort of gets you going in the subject, thinking about the non-equivariant situation you're dealing with. And of course, there's a big story that follows this, but okay, so here are some new theorems, relatively new theorems. So let X be a finite space over a cyclic P group. This is a theorem that appeared just in 2019. It was being talked about earlier, a couple of years before. If X is Kn plus 1 acyclic, the fixed points are Kn acyclic. So that there's a sliding, there's a move, a redshift, if you like such things. Right, that's the redshift direction, right? No, blue shift, that's a blue shift, okay. The 6 authors are Tobias Barthel, Hausmann, Naumann, all those guys, okay. And their proof is all in the stable equivariant category. They have a lot of fixed points. I don't know. I found myself wanting to understand their proof a little better. And so eventually, William and I have a proof that's very much in the spirit of what the textbook proofs of Smith's theorem. Like if you go to Tom Deek's book on transformation books, he has a chapter on this stuff, and he has a proof. And if you just run the proof, you can get something. And actually, if you translate, I mean, I've been saying things in terms of spaces, and if you went and I said it's, you could suspend and they'd be suspension spectra, and of course homology doesn't change. If you take what they did and try and say something about spaces, you realize they have to assume you have a fixed point in there in your space. And it's not so obvious how to get rid of that hypothesis. And our proof, yeah. When you say this talk about 6 weeks, I think that isn't right. I think what you said doesn't work. I don't think you can just add a base point and then play. I think. Yeah, but I think we'll talk about that anyway. Yeah, at any rate, that isn't my real point here. We prove a fixed point theorem on root. We show the thing does have a fixed point proof, but also the fixed point part of this assumes with X just finite dimensional, not just finite. So this is kind of, I said things we don't know. There's going to be a question at the end about finite dimensional actions on finite dimensional things. I should say in the history of the subject, people like Ed Floyd, they were studying actions of groups on Euclidean space, which is, and they wanted, so famously they showed you can give an action of the cyclic group of order 6 on like R8 or something like that with no fixed points. So this is an exotic topological action, right? Things like this. So they really wanted things to be finite dimensional, not just finite. Obviously, Lefschetz's fixed point theorem would tell you something about compact things and cyclic groups. But anyway, so there's an upgrade you can do that Chris and I came up with that says you get the analog of Floyd's theorem. So you learn something about all spaces. So that was kind of fun to discover. And as you'll see, we actually assume the first theorem and can deduce the second theorem from that, which is kind of interesting. So to sort of explain that, I want to talk about something more general. So as I stated, the classical theorems just for actions of a cyclic group of order P, but they get more general results using the obvious thing that if you have a normal subgroup of a group G, the fixed points under N inherit an action of the quotient group G mod N, and then the fixed points under that gives you the fixed points of G. So you sort of have a iterated thing. So you can imagine if X is acyclic, then Xn is acyclic, and so then you can use the theorem again, and so you can iterate these theorems, and in fact, you can get a version that the most general version would go like this: if X is a finite dimensional G space, G is a P group, and H is just any old subgroup, you could climb, since it's a P group, H is a sub-P group, you could climb your way up by cyclic groups, and each one being normal in the next, up to G, starting from any H. And so if XH is mod P acyclic, then XG will be mod P acyclic. So it's really just a restatement of the theorem, but it looks a little cooler, doesn't it? Okay, and Floyd's theorem similarly says the dimension would go down, okay? So, if you have a G space X, what are the, everybody knows you study it by looking at the fixed points, all the fixed point spaces, right? So you can think of, you start with a G space X and you get a whole list, a whole lattice really worth of subspaces, of fixed point subspaces, and maybe you want to think of them as being non-equivariant for something, or perhaps. And so the question is, can you learn about those, relate those things to each other, right? So now chromatic Smith and Floyd theorem. So what would a chromatic analogs of these things be? So suppose you have a fixed P group, a subgroup H, and somebody gives you M and N greater than or equal to 0. Here are two theorems about all finite G spaces X that might be true or they might not be true, okay? So the analog of the Smith theorem would be if XH is Km acyclic, maybe that implies that XG is Kn acyclic. By the way, I'm fixing a prime through all this stuff. Okay, so that would be, maybe that's true. Maybe whenever for that 4-tuple or 3-tuple, I guess, if G is fixed, right, maybe it's true, maybe it's not. Okay, and the Floyd theorem would say the dimensions of the homology goes down. Okay, so you're relating one Morava K theory of one space to a different Moravec theory on a different space. So, so here is one reason to be thinking about this. This first paper that got things going, published in 2017, that I think they were talking about it. I heard about it a couple of years before that. They identified the tensor triangular prime ideals of the compact objects in the homotopy category, in the G equivariant stable homotopy category. And so those are the points of the Balmer spectrum. And they sort of found them to be the things you would expect. They reduce composite order groups to P group case. And the punchline is you have a bunch of ideals and you want to know the topology of, you have the points and you want to know when these ideals are contained in other ideals. And that's exactly trying to determine exactly for which H, N, and M these theorems are true. Okay, that's the upshot. So answering which of these Smith theorems are true totally determines the topology on the spectrum. And they figured out what happened for the group C2 or CP. But anyway, but then other people, right? Okay, so here is sort of the theoretical part of what Chris and I did. So these are I'm just restating these things again. Okay, so you're asking when are these statements true for all finite G spaces, okay, or compact G spectra or whatever. And obviously the second theorem there implies the first because, I mean, you know, because it does. And so the interesting thing is the other direction holds too. If the Smith theorem holds, you automatically get a Floyd theorem. This would have been true, by the way, if talking about mod P homology, the proof works there too, and somebody, I don't know. So how do you prove that? Well, you prove the contrapositive. You show if you have a counterexample to the Floyd thing, so that says some dimension is not bigger than some other dimension, then you somehow have to construct a different space for which something's acyclic and something else is not acyclic. Okay, so that's what we do. I'm just going to say this very quickly here. Suppose you have an example that contradicts the Floyd theorem. There's a magic number D, and you can take a stable retract of D, maybe throw on a disjoint base point to give myself a base point. And there's a stable retract of that, and it will still be a finite G space that will violate the associated Smith theorem. And D depends on the size, just the size of Km of XH, and can be pretty big, like, you know, 2 to the 10th or something like that. Anyway, might be the retract is split off using an idempotent. So this is an idea that was used once before in topology, the proof of by Jeff Smith of that got the machine rolling in proving that every space has a VN self map. He uses this idempotent. It's in Appendix C of Doug Ravenel's book. You can also, I actually use, but our paper has references and includes some references that weren't around when Doug wrote his book. I think that would be useful, especially at odd primes. Anyway, so we have this thing. So notice, by the way, just to put this in context, if you're looking at the Moravec theory of a product of a space with itself, it's like taking the Moravec theory, it satisfies a Kuhn theorem. So you're looking at a vector space tensor with itself d times, and it's acted on by the symmetric group. And there are a lot of algebra people who think about this action, and maybe you can find an idempotent and split off a piece. So this is the sort of thing representation theorists know about. And anyway. So, so that general question of when those things hold, that would when those Smith theorems hold, it turns out you can reduce it pretty easily to the following thing. You define a number to be the smallest r such that that Smith theorem is true, okay, such that what I wrote down is true. And the goal is to sort of compute those numbers. If you could do that, you would have solved this whole, for a fixed G and all its subgroups. You could deduce various things, and it's written down. I mean, Chris and I sort of summarize some things in our papers, and you can find them both in the paper of the sixth author paper and the paper of Balmer and Sanders. Between those two papers, they get a lot of things, the conjugacy classes, this, that, and the other. And anyway, anyway, this is the goal. Okay, and so this is restating their theorem. This blue shift number is at most 1. Okay, right. So you can iterate it just like in this, using that normal thing, but it's a little more complicated. So you have to define a funny number for a group and a subgroup, and you define it to be the smallest r such that you can climb your way from H to G by normal subgroups, and each one is cyclic. So these are all p groups, right? So cyclic p group. Okay. If G is abelian, this would just be the rank of the quotient group, just the number of generators you need to generate the quotient group. So it's sort of a generalization of rank, but it turns out to be a pretty weird function. For instance, it's not, as you pass to from bigger groups to smaller groups, if H is replaced by a smaller group, you might think the number is going to go up, but it doesn't have to. It can go down and up and down. So it's a slightly weird thing. And we give an example. Well, there's some simple examples in our. We give examples of every weird thing that can happen with this function in our paper. Yeah, it doesn't. It behaves a little bit strangely on products of pairs and things like this. Anyway, blue shift conjecture is that. So let's see. What did I just say before? I said, oh, we have this group theoretic upper bound, right? Oh, here, I got to use this thing, right? There's a group theoretic upper bound for these mysterious numbers we'd like to compute, these blue shift numbers, right? And so why don't we just conjecture that's best possible? All the proofs of, I mean, both Williams and this, my proof and the sixth author paper and any other proof that anybody comes up with always involves classic localization theory to relate the fixed points to the original space. And that only works really well with, you know, complex oriented theories. You have Chern classes to invert and stuff like this, and Euler classes, and spaces being abelian really helps, and cyclic is abelian, and so you sort of think there's no idea that anybody can come up with that would improve upon this. So you better conjecture it's right. Okay, so that's so you need to show. So you have this upper bound, and you'd like to show it's met by a lower bound, and yeah, okay, and so just translating what it means to show that this mystery number RNH is bigger than a number R means you need to find a finite G space such that the H fixed points are acyclic on that one, so it can't be smaller. So, but the G fixed points are not acyclic. So that's what it means. So it's sort of hard to find like just a space lying around that's acyclic in one of the, you know, like in the fifth Morava K theory, and then it's an action of some group, and then suddenly it's, you know, the fixed points are, you know, not rationally acyclic. I mean, how are you going to do that, right? So it's sort of hard. So the sixth author folks find one example in the literature that works for the pair elementary abelian group, CP to the RE, and it's that Gregorone and Catherine Lesch had analyzed something or other, and you can interpret as telling you, you know, this example can be used to show this thing. And their example is a variant of actually what Steve Mitchell did all those years ago. So, so it's some old ideas there, involving the general linear groups, not the symmetric groups, by the way. Anyway, so, and You get certain obvious conditions. You're looking for examples. If you can always pull back an example from a quotient by a normal group. So that gives you a lot of inequalities as well. So this one example with these elementary abelian things, since any abelian group projects onto an elementary abelian group without changing the rank, these suffice to actually show that the lower bound equals the upper bound for all G abelian. And in fact, I can write it down here fast. The general bound that one example gives you is that Rn of GH would always be bigger than R of GH, and then you throw in its Frattini subgroup of G. So this is a bigger group. So that's the normal subgroup of this, such that the quotient is the maximal elementary abelian quotient of G. So you sort of have this thing at this point, GH. So this is this general bound, projecting that OQs that, and this one example gave you that thing. So when we were first looking at this, we were looking at the first example where these were different. They agree for abelian groups. The first example where it didn't agree was when G was the dihedral group of order 8, and H was a cyclic group of order 2 that's not central. And this number was 2, and that number was 1. So there's this question. So the 6 author folks are left, but that's the first example that can't be handled. And so, okay, so the easier way forward, you just have to find, remember, we're trying to find things that sort of violate what would be the Smith theorem, but you can just find something that wouldn't work for the Floyd theorem. So it's easier to find just maybe a more familiar space that you can calculate and just see something is bigger than something else. And that's what we did. Yeah, so we look for these first examples that you couldn't figure out from other examples. And I just gave you the first example of such a essential pair besides the elementary abelian one. So first of all, we found some x's quite easily. Didn't have to use the work of Greg and Catherine, who were channeling Steve Mitchell. We were able to do that. And then we found the dihedral group turned out to be one of a infinite family of the extra special groups. There's a positive extra special. They're all always extensions of an elementary abelian group of order 2 of rank 2R by it's a central extension by a C2, and there's some form in there, and it's either positive or negative. So there are 2 of these groups, and these were the interesting ones for this point of view, and is a very nice subgroup. This WR generalizes that non-central C2 I told you, and so our X. So this is the fun part. Our X's. So this is an idea to like search for this, and Chris just searched with computers and databases of representations. We found some. We just took representations of our group G, a real representation. Then you take the space of lines in there, and then what are fixed points? It's just like the one-dimensional space of one-dimensional sub-representations and things like this. So you can have a lot of fun computing, and it's dead easy to compute Morava K theories of projective spaces, because these fixed points are always like disjoint unions of I guess it's just disjoint unions, in this case, just disjoint unions of projective spaces of different sizes and stuff, depending on the one-dimensional representations in V when you restrict to H. So it was rather fun to work this out. So we were able to get this big infinite family. Good. So here's open problems. So towards the blue shift conjecture for all finite P groups. So when I was in Cambridge, as has been alluded to about a month ago, I was there for 4 days and was chatting with Tobias Barthel, and there was I guess I'd heard rumors that maybe somebody was working on proving this conjecture, and he said he thought Robert Birkeland was doing this with some other folks, and so I actually sent Robert an email and said, particular, oh yeah, these are some examples that we couldn't get. The first one is group of order, the dihedral group of order 16, and again, it has a central subgroup of order take a non-central subgroup of order 2, and the lower bound that we get from our work gives you 2. The lower bound from the 6th author paper would have been 1, but the upper bound is 3, so there's a difference there, and there's just no way to mess. There's no representation. There's no gimmick that works that we could find. Anyway, so that's really one of the first really interesting examples for various reasons, and I have another one there. So I wrote him an email, and Robert an email in late May, and this morning at 8:50 in the morning, I got an answer. Read it, and he said, "Yeah, we could do that. We think they have a general periodicity theorem." With Marcus Hausmann, Ishan Levy, and Leonard Meyer, and he was asserting that this is general enough that you can construct anything. So I think they're asserting the conjecture is true. That's really cool, which will totally determine this thing. I'm a little curious because I asked him specifically about this, and he said, "Well, you construct the second example," and he said, you know, he sort of outlined, this is an email, right? You construct something by induction, you start with a sphere, with a trivial action, and you do something, so the fixed point to this and the other fixed point to that, and then it's a V1 periodic map on those, and so on. And he comes up, but I still don't quite understand how it works, I must say. A 3-line email didn't quite suffice, but anyway, so it may be that mainly because this number RGH is kind of a weird number. I mean, unless things are abelian, it's rank. It's some sort of rank-like thing, but it isn't really. And so I don't know if they have to learn something about representations of a group, how that's related to that. It feels like that's going to be part of the story, but I don't know. We'll find out. But anyway, that might be done. As I say, they have a new way to find examples, just like Mike Hopkins and Jeff Smith found new ways to find type N complexes, right? Just take VN cofibers of VN periodic maps, and you get the next guy. Okay, so right. So let me end with one other thing. My theory with my proof with I mean with William, we were just holding on to the assumption that a group acted on, the cyclic group acted on a finite dimensional space, not a finite space, for a long time. And it works, and we're going through a proof so long. You start by saying if it's Kn acyclic, it's acyclic in the Morava E theory cohomology, and then you do an Borel cohomology thing, and then you do standard localization, and you get rid of all the equivariance, and you're left with this question, which is somehow you have your fixed points, and you'd like them to be acyclic, and they're acyclic in En plus 1 theory after you invert Vn or something like that, and is that enough to say it's acyclic in Kn theory? And that's kind of where we're stuck. But they're first of all, it can't be true all the time, because a Moore space is K1 acyclic, but not K0 acyclic. So you can give it a trivial action and it would violate all this stuff. But that's not an equivariant problem. And Bousfield showed, you know, Ravenel had, this is my last thing I want to say. Ravenel showed if you have a finite complex and it's acyclic in one Morava K theory, then it's acyclic in the previous ones. Okay, so Bousfield showed the same thing holds for all spaces, not spectra, spaces, as long as you avoid the previous one being 0. Because he never mentions why he avoided this. He never points out, oh, it's wrong there, but so he just has n greater than 1 or something like that. And it's sort of a crazy proof. Steve Wilson had a similar, had in the same proceedings, their papers are back to back. He has a proof of the same theorem, but he has a finite type hypothesis for some reason. And it seems like finite dimensional and finite type are going to like make you think finite. So I really want Bousfield's proof. So we've been looking at, I mean, William and I have been looking at Bousfield's proof, and it gets into funny questions about when is there a localization functor that turns certain maps into isomorphisms, and anyway, so it's kind of crazy. Anyway, but that's an open question. We state it in our paper. There's another open question in our paper that we also state, but anyway. And these are some of the papers which have all come out lately. So that's nice. I have another paper with Chris Lloyd, which is some applications of this stuff. And I think that's it. Thanks.
Questions? You're at the end of the day.
Could you go back to the slide?
Yeah.
No, that's not.
This one? Right, yeah. Oh, yeah. So anyway, it's really fun to see this very classic thing that was classic when I was in graduate school sort of come back to life as stuff. Let me show you one example. I have to show you one example. This is for Dennis. Okay, so let M 5 be the space SU3 mod SO3. So this is this 5-dimensional manifold, and it's the simplest manifold that is odd-dimensional manifolds that's not the boundary of anything. And its mod 2 homology cohomology has something in dimension 0, 2, 3, and 5, and square 1 takes you from 2 to 3, and square 2 takes you from 2 to 5. So it's the question mark people sometimes call that cohomology, and it's not a mod 2 homology sphere, but it is a mod 2 K-theory sphere because of that Steenrod operation that knocks out two things. And so classic Smith theory would tell you a homology sphere of fixed points are a homology sphere. So you learn any action of C2 on this space, the fixed points have to be a rational sphere. So I think that's new. I don't know. So that's kind of so there are a few sort of concrete examples you can get out of this stuff.
There's a comment about this. Oh, something.
No, there isn't. I think.
No. So that manifold has the smallest homology possible, which is not a sphere.
Yeah.
The integral coefficients.
Yeah. Right.
G2,
That's right. Yeah. It's a lot of
So
interesting for me.
Are there any other manifolds?
Yeah.
Like
No.
that?
I think this is the only one. I think this is going to be the only one that's out there that's a K-theory sphere. Yeah. No. Yeah. No. Yeah. No. I don't know.
With only one Z2 just below.
I don't know. You run into a lot of problems.
Because it's a question in the course, and it turns out you could start proving it in some cases, and then Martin Van Dursky came along and added some more stuff, and we proved it. So we're going to write a paper. There's a unique odd manifold in the world that has the smallest homology.
Okay.
In any dimension, it's 4K plus 1. And I mean, it has to be 4K plus 1.
Okay.
And that's diffeomorphic to that one. And then we couldn't write the paper because it turns out Bill Browder proved the same result in 1960.
Okay. There we go. Those old guys knew a lot. Yeah. Those old guys knew a lot. Right.
I was just going to follow up with this. You mentioned spheres. So part of Smith theory is about fixed points being spheres. Does this chromatic fixed point theory work for that as well?
Yeah. Well, yeah. You get in my paper with Chris, we sort of deduce there's an Euler characteristic even odd thing going on as well, but we are able to deduce if something is a Kn homology sphere, then the fixed points are a Kn minus 1 homology sphere, and if a bigger group, you'd have the shift. Yeah, right. So it works. It's just the same. Yeah. So it's rather fun. And this is about the only concrete example I can give that's very obvious. Sitting there as a manifold.
Let's thank Nick again.
So, okay, the bank is open for the student special.
I gave my talk, I used up all my energy.
The dinner
Oh,
starts
that's,
at
yeah, right. It's,
6:30
there's a.
and it's in Hart House.
Which
Up-
entrance?
Tia
Hart,
told me this
the
problem
entrance that
in
you meet
1968, and I think
coming
he was
up
working on-
from here.
Art House Theater.
Sorry?
Does it say theater on it?
That is part of Hart House, but you want the Gallery Grill,
Okay.
the Hart House Gallery Grill. Okay. To get to Hart House, to get to Hart House, it's that way. Well, there'll be a group going, just tag on. At any conference, when you have a group of people going to a restaurant, no single person in the group knows how to get there, but the group as a whole always succeeds. That's a theorem. That's a theorem. Thanks.